All right, I'm back. Still on page 206. Things seem to be working right now. I mean, I have the iPad up. We can see the notes. We're only going to stay on this for a second, and then I think we're going to jump to Desmos and take a look at some patterns. But we're going to talk about some common polar curves. So the most common polar curve is r equals a constant. It's a circle centered at the origin. Takes 0 to 2 pi to trace out the whole thing, just like the unit circle takes 0 to 2 pi. So that's actually the most common. The next most common is probably those other circles that we talked about, like r equals diameter times cosine, r equals diameter times sine. It's really the directed diameter, so like sometimes positive diameter, sometimes negative diameter. Think of it like vectors with a direction. And those are centered on an axis tangent to the origin. Those are like the next most. The next most common, I would say, are rose curves. Rose curves look really neat. They don't particularly look like roses to me, but whatever. So they all have equations that are very, very similar. And you have to be really careful, right? So all rose curves have equations that look like r equals a. So you get a, and then you get either sine or cosine, doesn't matter which, n times theta, but n must be an element of the positive integers. So if n is negative, it's not going to be negative, because what you're going to do is you're going to factor that negative out using even and odd properties of sine and cosine, of cosine and sine respectively, I guess, because cosine's even and sine is odd, whatever. So a can be any real number. It can be positive, it can be negative. It shouldn't be 0, so let's say any non-zero real number. And then n has to be an integer. If it's not an integer, you do not get a rose curve. You get like something crazy. So what patterns can we potentially see here? So I've put 4 examples here, but it's better to play around on something like Desmos or GeoGebra or your calculator and just like look at a lot of examples. But let's look at these to begin with. So here's r equals 7 theta, sine of 7 theta. What am I talking about? R equals sine of 7 theta. So first thing I notice, it can be sort of difficult to count them, but there are actually 7 petals. 1, 2, 3, 4, 5, 6, 7. So we get 7 petals. There are no petals on the x-axis. There is a petal on the y-axis. Don't focus on that too much. Focus on the fact that there's no petal on the x-axis. You'll see why. Here we have r equals sine of 8 theta. Okay, so who wants to count these? We got, well, there's 4, right? That's 4 petals. And then there's, in 4 quadrants, that's happening. So there's 16 petals. So that's maybe interesting. We had sine of 8 theta, we got 16 petals. We had sine of 7 theta, we got 7 petals. Maybe it's the case that odd numbers will give us an odd number of petals, or the number. Like if you have 2n plus 1 as the coefficient of theta, it looks like maybe you get 2n plus 1 petals. It kind of looks like if you have an even number, you get double that for the number of petals, maybe. Also, this is sine, no petal on the x-axis. So I should actually write that somewhere. So no petal on x-axis. And this, again, no petal on the x-axis. So this one, you'll notice, also no petal on the y-axis. But that's why I told you, don't focus on that. It's really, is there a petal on the x-axis that makes a difference for these in terms of looking at the graph and figuring out the equation? We'll see why pretty quickly, why this is the case. Here we have r equals cosine of 9 theta. So cosine of 9 theta. So n is equal to 9. Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9 petals. And there is a petal on the x-axis. Petal on x-axis. Okay, so cosine, and there is a petal on the x-axis. 9 petals, and n was equal to 9. So an odd number gave us the same number of petals. Let's see if this even number 6 gives us 12 petals. That's what I'm expecting. Also, I really don't want to count that, but we'll see. All right, so first off, definitely petal on the x-axis. So petal on x-axis. So it looks like you can tell the difference between a cosine and a sine graph based on whether or not there's a petal on the x-axis. If there's a petal on the x-axis, it looks like it's a cosine graph, which again feels right because x goes with cosine. X's are cosine. Like x and cosine have they're entangled when you're talking about polar. So petal on the x-axis, you immediately know you're dealing with a cosine thing. It looks like if n is odd, you get that number of petals. Looks like if n is even, you get twice that number. So here, how to count this? I see 2 full and 2 half petals in the first quadrant. So I'm going to say that this is 3 petals. And there's 4 quadrants, so we get 12 petals. Okay, so it looks like we're able to sort of generalize a couple of things here. That if there's a petal on the x-axis, it's cosine. If n, the coefficient of theta, if n is odd, you get n petals. If n is even, it looks like you get 2n petals. So these seem to be things that are just kind of happening. We didn't investigate A. Let's go to I'm gonna go to Desmos, I think. And do I have a browser open? Hold on, let me open a browser and then we'll go to Desmos. So I'm gonna share this. I think screen sharing failed to start. Oh God, what does that even mean? Share this, and then, okay, so let's go to Desmos and let's start graphing. And what I want to do, I want to like create a polar grid. So I'm going to click the wrench in the top right and change my grid to a polar grid, which is totally fine. Like it just does it instantly. That's amazing. So R equals, you know what I want to do? I'm going to do like A times sine of n times theta. Okay, and I'm just going to let it create sliders for those. And then what are my options for the slider? I'm going to change this step to 1 because I definitely want to count by ones. And here I'm also going to change this step to 1. And so I think if I change these, yes. Okay, so right now n is equal to 1. So I'm just getting circles that are centered on the y-axis, which makes sense, right? Because it's a times sine of theta, and we already knew that. Let's change n. So here, n is, what are we doing? Okay, n is 2, n is 3, n is 4, we get 8, 5, we get 5, 6, we get 12. So that's doing basically what we thought. Now the real question is, what is a doing? And can we tell? So here, a is equal to 8, you can see. And here, this circle is 8. So it looks like the curve is inscribed in a circle of radius 8. Let's change it to 6 because that's the next grid line that's nice. Here we change it to 6 and it looks like the curve is again inscribed in a circle of radius 6. Let's change n and see if that like remains true. It does. Okay, so it looks like we kind of know what we're doing. So I'm going to change this to cosine and just like make sure everything still works. So now we have cosine. I want to change, so it looks like if I change this to 7, whoop, 7, go. It looks like, yeah, we're right between 6 and 8. So 7, this is inscribed in a circle of radius 7. Let's make sure if I change these, it stays that way. And it definitely does. So I think we know what the patterns are. So what I'm going to do is try to go back to the iPad. I'm having some trouble with screen sharing right now. Hopefully this works because, man, I don't want to start again. Here we go. Okay. So I think we can make generalizations. So I think we should. All right. So A, we saw, was the circumference, no, the rate, oh my God, circumference? Where did that even come from? Radius of the circumscribing circle. So the entire graph can be inscribed in a circle of radius A. So maybe I'll actually write that. Also, my little picture is in the wrong place. Let me move myself back up. So it's in circle R equals A. So you can draw the whole thing inside the circle R equals A. Then we have if n is odd. So if n is odd, you are going to get n petals. If n is even, we found that you would get 2n petals. And then it doesn't ask this, but it really should. We also found that if cosine, then, so if cosine, then petal on x-axis, if sine, then no petal on the x-axis. So on x-axis, I was gonna talk and then I realized I can't like spell right. I can't write and spell and talk at the same time. Like no one could do that. All right, so that looks terrible, but hopefully you were taking your own notes as I was saying it. So it turned out the y-axis was inconsistent. Like you can't rely on the y-axis to tell you if you're dealing with sine or cosine. But the x-axis, 100% of the time, cosine will have a petal on there and sine will never have a petal on there. So the x-axis is consistent. So what I'm going to do now is really quickly just graph these. This is review. If you're not familiar with this, go back and watch. I don't know. I have videos. I haven't gone through the notes yet, but there are definitely videos on graphing trig functions. I use a method that is like pretty straightforward. So if you're a random person, do that. Otherwise, here the period is 2 pi over 2, which is pi. So the increment is going to be pi over 4. And then we go up to 2, down to -2, and it's positive sign. So here's pi over 2. I'm not going to label everything. So here to here to here to here to here. You actually, so for reasons we don't understand yet, you actually need to keep going until 2 pi for this one. And maybe, but oh my God, did you see that? Totally missed. Also, my scale is like all messed up because I added that stuff at the end. I didn't like think it through. Have a plan, people. Execute the plan. That's not me. There we go. Okay, so why did I think that I would need more? I don't know, but maybe I was thinking that this is 2, so 4 petals. Do you see anything in this picture that looks like it might be 4 petals? I see things that look like they might be 4 petals. Maybe this is a petal. Maybe this is a petal. This could be a petal, and this could be a petal. So I knew that I was only going to get 2 potential petals if those are petals, which, spoiler, they are. So I knew I had to keep going. Let's take a look at this one. Period, 2 pi over 3, increment, so 2 pi over 3 over 4, 2 pi over 12, pi over 6. All right, so I know that there should be 3 petals. So let's see what we need to make that happen. So 2 pi over 3, gonna cut, cut, cut. And if I start graphing, so it's positive cosine, so it starts at a max here. I see this is only 2 petals, right? I mean, it's 2 like discontinuous petals in the event that, in the wink wink event that they're actually petals. I'm currently seeing, let's use a different color. I'm seeing 1 full petal, and then I'm seeing half a petal, and then another half a petal. So this is 2 petals, but like not 2 nice continuous petals. I need 3 petals, so I need 2 more increments. And if I go, so it's pi over 3, 2 pi, this will be 3 pi over 3, which is pi. Maybe that's a thing. Here to here, boom, boom. So I added these in, so I'm gonna use a different color. Here's the end of this petal, and then here's the end of actually this petal and this petal. That closes that petal. But anyway, we're going to find out what all this means. I just wanted to review that really quickly because the next thing we do, 100% based on your ability to graph these rectangular things. If you're not good at that, go and spend some time getting good at that before you even bother with the next thing, because you need to be able to do this really well to be able to graph in polar. So I'm going to stop this here. I will hopefully see you in the next video, and I hope you're finding these helpful.